short video presents a snapshot of the project Plastic Monitor, one of the projects of ESA's discovery campaign on remote sensing of plastic marine litter. Plastic Monitor is about detecting riverine plastic conglomerations, fluxes and pathways in Indonesia. It was conducted by Deltares and River Recycle, and it was supported extra in the field by the Bening Foundation and Waste for Change. The presentation is by Marieke Eleveld, Joanna Miravaiga, Hiska Akmalia and Kodontam Situmohang.
It is estimated that around 10 million tons of plastic waste enter our oceans every year. And while a lot of attention has been given to plastic pollution in the marine environments, more recently we started looking at rivers, as they are major pathways of transport of plastic waste from land into the sea. However, even if these global estimations are very valuable, they come with a large degree of uncertainty. Most importantly, our knowledge in what concerns the sources and the quantification of these leakages remains very limited. And this is exactly the type of information needed to make the case for policies and targeted measures. So the underlying question that Plastic Monitor set to answer is if and how remote sensing can contribute to address some of these knowledge gaps. Our project focused in Indonesia, which is a country that has particular challenges with plastic pollution. It is the largest archipelago and the fourth most populated country in the world, with a population of over 276 million people. Every day, the country generates over 100,000 tons of waste and a staggering amount of 7.8 million tons of plastic waste per year. However, half of this amount is considered to be mismanaged, meaning that it is either disposed of in inadequate landfills or is not even collected in the first place. And as such, people need to get rid of it by either burn it, bury it, or discard it directly into the water. This has resulted in 350,000 tons of plastic waste estimated to be released into the sea every year, and more than 80% of this amount is discharged by rivers. This is one of the reasons why Indonesia was put in the spotlight as one of the largest contributors to plastic pollution. The Indonesian government has committed to address this problem and has set up very ambitious targets to enhance waste management and reduce plastic pollution. However, it remains challenging to measure the progress towards these targets when there are still major limitations in terms of monitoring the sources and the quantities of plastic pollution. Our motivation was to use real field conditions to prospect the potential of applying Earth observation technologies to detect and quantify plastic litter in rivers, since rivers can work as sentinels of plastic releases into the sea. And the key questions that we addressed: can we distinguish large accumulations of litter in rivers? And in the absence of field observations, ensure that this consists mainly of plastic? And how can remote sensing enhance our knowledge of plastic pollution by complementing and strengthening other data tools in order to better inform policy?
The main objective of Plastic Monitor was to assess whether we can detect heavy plastic pollution loads in a river in Indonesia with satellite imagery. And also to demonstrate how remote sensing can enhance the quantification and monitoring of plastic input into the marine environment. To investigate this, we broke it down into specific objectives. The first one was to characterize the naturally floating debris and plastic litter composition in the accumulation patches in the Indonesian Citarum River. We did this by sampling. Secondly, we deployed time-lapse cameras over the river and developed a plastic detection technique to characterize fluxes of floating debris items. And from these cameras, we also had additional field data to monitor the patches. Then we used satellite imagery targeting the known floating debris accumulation patches in the river, and we compared what we saw on the satellite against the known debris composition from the sampling. Also, we wanted to discuss the potential of these remote sensing platforms in enhancing our knowledge of plastic pollution, and particularly for the policy formulation. And finally, we provided recommendations for future sensors tailored for plastic pollution. Our study area is the Saguling Basin on Java, Indonesia. It is where the Citarum River streams from the southeast from Bandung northwest, and further downstream the river turns northward to end up in the sea east of Jakarta. The dashed yellow line in the bottom image indicates our Site 1, where we conducted a lot of research. The annotated red dots indicate our reference site, Site 3. The general setup of our experiment comprised of 4 elements. Using the existing hydrological conditions, River Recycle deployed the cleanup system in the river to intercept, accumulate, remove and quantify riverine, litter and other debris. Their booms created large patches of naturally occurring floating litter with known volumes and composition that we could use as ground truth and match with images of the satellites that orbit above it. They also deployed cameras over the river to collect images of floating debris passing through. Time series of riverine litter data from these cameras helps us to determine the fluxes of plastic and validate other modeling approaches because it gave us more insight into the hydrology.
There were 4 sites selected that met the requirements for this project. Site 1, which was also the main site for River Recycle's river cleaning operation, where a 300-meter boom was installed across the river to stop, accumulate and remove floating debris. Site 2, Batu Bridge, further upstream to the east, for in-situ time-lapse cameras and physical sampling. Site 3 is opposite of Site 1, to contrast Site 1, and later also used for experiments with bamboo frame or waste trap. Site 4 is an opportunistic site at a location where a floating bridge captures debris before it reaches Site 1. All the sampling activities began in September at Site 2, followed by Site 1 and 3 in November 2021. Between the months of December 2021 until January 2022, steady waste accumulated at the boom at Site 1, in combination with some water hyacinths. Physical sampling could still go on quite effectively. From February onwards, overwhelming water hyacinth growth was experienced at Site 1, putting extra load pressure to the booms, and it became more difficult to extract waste samples from the dense water hyacinth mats. Photo and physical sampling at Site 2 began in September 2021 with Sector 9 bamboo boom in place under the bridge. The bamboo boom broke down in November. Physical sampling was discontinued and moved to Site 1 and 3, while photo sampling continued for some time. Because of the persistent presence of water hyacinths, decision was made to experiment by putting mainly plastic debris from the river in a 10 by 10 meter bamboo frame at Site 3. The frame was constructed in March at Site 1 and towed to Site 3 to be placed and used till end of the project. In February 2022, a floating footbridge was constructed by the local community about 3 kilometers upstream from Site 1. This footbridge was also identified in Sentinel-2 data. It was accumulating debris and stopping part of it from reaching Site 1 farther downstreams. This was found opportunistic for sampling activities, and so it became Site 4, where sampling was started in August 2022. In each of these 4 sites, we took periodic samples of the accumulated debris between October 2021 and August 2022, although the sampling period varied between the sites. The items were classified in 8 categories of material, and the plastic category further specified into 5 groups. Note that we considered all sorts of floating debris, including non-anthropogenics such as wood, lumber, twigs, etc., since these are relevant in the context of EO research. We refer as litter to the anthropogenic debris. for example, human-made or synthetic or processed items. Soft plastics is a category that includes a mix of items such as plastic bags, mostly polyethylene, but possibly other polymers that we cannot distinguish by observation alone.
We deployed a time-lapse camera at each site. The picture on the right-hand side shows how the field team prepared to deploy the camera under the bridge. The camera under the bridge is installed in the middle of the river, pointing at an angle close to nadir, to record the movement of the floating debris. You can see the illustration of the method on the left side picture. We perform lens calibration before we place the camera under the bridge, and also georeference the field of view by measuring the scene with a handheld GPS so that distance in the image becomes an absolute measure. In this way, we can extract statistics on floating debris based from the image of the time-lapse camera. The software of this method is available at this link, or you can also scan this barcode. We also analyze satellite images. We match the in-situ sampling with the satellite image overpass. GPS coordinates of the sampling locations were used to extract spectral signals from Sentinel-2 images and the backscatter from Sentinel-1 image. We compared the spectra with the field data about the collected and categorized debris and water hyacinth.
We also calculated spectral indices from the extracted spectra. These have the advantage that they somewhat compensate for biases by solar angle or suboptimal atmospheric correction. The normalized difference vegetation index describes the difference between the reflectances in the infrared and the red. For vegetation, the near-infrared reflectance is high and the red light is absorbed by the vegetation for its photosynthesis. The floating debris index by Lauren Miron works by leveraging the difference between also a near-infrared reflectance and the baseline, and it proved to be efficient for detecting floating debris. This is depicted in the graph below. In the near-infrared, floating debris has a high reflectance against a background of water with low reflectance because of the water being highly absorbent in those wavelengths. The table and the other graph on the right-hand side show the indices for the actual sampling points from the previous slide. And if you start to plot normalized difference, vegetation index, NDVI against FDI, floating debris index, we see that water scores really low on most indices, water hyacinth scores high, and the floating debris, it ends up somewhere in the middle. Besides optical satellite data, we also use microwave Sentinel-1 synthetic aperture radar data. At first sight, we can distinguish in these images a black river with white land with lots of speckle. That's the grainy texture in these images, and that is caused because the backscatter coefficient is a vector summation of all the signals that scatter in a pixel. Radar measures the roughness and the dielectric constant, and that's the degree to which the objects reflect the C-band radar signal. What would the signal of floating debris be? The SIG has a low dielectric constant, so the signal, the radar signal, may pass right through. Our experiment provided insight here as well. If you look at the red ellipses in the images, in these ellipses there is the boom, which you also see in the photos below. And these images and photos were taken just days apart, end of November, middle of December. End of November, there was no debris yet captured by the boom, whereas middle of December, some debris was captured, and we see a higher signal, so white pixels in the red ellipse. The images below are from the time-lapse camera, so they are really useful for these kind of validation practices. And now we know debris is rough and there's a higher scatter than water.
During the project and throughout a period of 11 months, we have collected a really large amount of field data on riverine debris. We sampled almost 58,000 items between October 2021 and August 2022. So a period that is covering both the wet as well as the dry season in Indonesia. And apart from the use of these data as ground truth for remote sensing, this information can provide really valuable insights to help us understand what is the type of waste that is flowing down Indonesian rivers. So when looking at the results of the composition analysis, we see how dominant plastic is. So covering almost 75% of the total debris, including naturally occurring vegetation and woody material. And within the plastics category, we see that approximately half of it can be attributed to what we called soft plastics, which is most likely polyethylene, but can also include other polymers that we were not able to distinguish just by observation. And then 20% of EPS, or expanded polystyrene, or styrofoam as is commonly known. And this colorful mix of plastic, of combined plastic polymer with a thin layer of aluminium. This is where we find a lot of sachets, which are massively used in Indonesia. And then we have these two less represented categories, which is the high-density polyethylene, which is a very hard plastic, as well as PET, which is commonly used in water drink bottles. When we look at how these different proportions of plastics change over time, so throughout the 11 months of sampling, we can actually see some interesting trends that can potentially be related to seasonality as well as reflect patterns of rainfall and hydrology. So we see that the percentage of EPS, here in gray, tends to decrease as we move from the wet season towards the dry season. And in contrast, the percentage of soft and multi-layered plastics, here in blue and yellow, they tend to increase. Another interesting aspect is that the fractions corresponding to HDPE and PET, they remain fairly unchanged throughout the period, but always relatively low. So this data may help us understand what are the factors that are at play and that affect the composition of the litter that we find in rivers. For example, EPS, extended polystyrene. We know it's widely used in Indonesia as packaging of electronic material, as containers of fast foods, and we know it's a very light and it fragments really easily. So these characteristics may actually help explain why during the rainy season we tend to find higher proportion of EPS in the river than compared with the dry season. And this may be a result of rainfall as a mobilizing agent that is transporting EPS fragments from land into the river and then downstream the river. We can also see the influence of certain policies that are targeting plastic or plastic waste. For example, as seen before, we've seen that the percentage of PET and HDPE remains fairly unchanged and always low, and these are exactly the types of plastic that have a high recycling value, and as such, they are intensively scavenged by waste pickers, being it on dump sites, but also in rivers, as we see in the picture. We also see that the other two categories, so EPS and multi-layered plastics, they are massively used and they tend to either be difficult to recycle or not recycled at all. And therefore, this is a type of materials that waste pickers tend not to collect. So this data shows how important it actually is to have this detailed information on the occurrence and the characteristics of the litter and how this change in time. So to help us understand what are the factors that actually influence how much and what types of litter occur in the riverine environment, but also how policies are actually influencing this occurrence. And what we see as a trend is that, generally speaking, when we have a plastic material that has a high recycling value, we tend not to find so much of it in the environment. Contrary, the type of plastics that have very wide applications and extensive use, for example, the sachets, which are single-use, unidoses packaging, and that have little value for recycling, we find a lot of these in the environment.
Delta has also developed Python code for analyzing the images of the time-lapse software. It is a prototype software for extracting statistics on floating debris using computer vision techniques and pixel-based detection to extract statistics on the floating debris at Site 2. But what can we learn from that? The software generates a video highlighting the debris passing through a selected zone in the frame, as well as statistics about the total number of items, debris items, the total area in pixels or in aerial units, and the fluxes of the debris items. We've also seen its strength for validation, and now we see that we can learn from its statistics of floating debris, based on the images of a simple RGB time-lapse camera. The camera made no measurements outside the optical wavelength range, so in that sense it's different from the satellites, such as, for example, Sentinel-2. There are of course also some limitations from taking this simple approach, so it's difficult to discriminate between debris and non-debris items. One needs the extra images to see whether something else was passing under the bridge, like the boat. The software will also be affected by sunglint, because computer vision techniques look for bright items and also rain splash and these kind of things. But all software was developed for research and is distributed under an MIT license, so without warranty, but in the hope that it can be useful for further research, for example, for citizen science. Having everything neatly in place, with also the multispectral instrument on Sentinel-2A and B, anti-synthetic aperture radar on Sentinel-1A monitoring our study site, field conditions at Site 1 changed rapidly. And on this end of March radar image with an inset and complementary in situ time-lapse camera image on the right, you can see that we cannot discriminate the floating debris and plastic from water hyacinths anymore at Site 1. So it was really time to move to our reference site, Site 3, which was not infested by water hyacinth. And in August, we collected all riverine floating plastic debris in a 10 meter by 10 meter bamboo frame and studied that further, matching the fieldwork with tasking very high resolution satellites such as the ISI, X-band, Spotlight radar data.
This slide shows the backscatter from an ISI Spotlight image of 22nd of August 2022. The 10 meter by 10 meter frame filled with plastic debris from the river at Site 3 shows up as a bright area on the image. Sampling point locations, which supposed to be inside the frame, appeared outside of this patch on this ISI image. Location accuracy between phone, GPS, and ISI was off up to 9 meters. This can be due to the inaccuracy of the GPS from the phone and the geometric inaccuracy of the standard geocoding of the ISI image. A corresponding Sentinel-2 image that also passed over on the same day of 22nd of August 2022 has a coarser spatial resolution compared to the ISI image. However, the plastic in the frame is still recognizable by the very bright color around the sampling location. From these bright pixels, we extracted the spectral signals and we calculated the NDVI, NDWI, and the floating debris index or FDI. Several objects such as water and water hyacinths were also extracted from individual Sentinel-2 Level 2 images. Their NDVI and FDI values were plotted together with the NDVI and FDI of floating debris like plastic and other floating objects. This graph shows the extracted FDI and NDVI from different sampling days. Each sampling day had an image acquired under different conditions such as view angle, solar angle, atmospheric, weather, and river conditions. However, grouping in the main classes, water, water hyacinth, and floating debris can be distinguished. The frame, which is full of riverine plastic debris, are around the range of minus 0.1 to plus 0.2 for the NDVI, and the FDI is around minus 0.1 and plus 0.1. Using this range of NDVI and FDI, we can create an indicative map of floating riverine plastic using thresholding in the raster processing. This is the resulting floating riverine plastic map from the classification sampling date of 22nd of August 2022. The red areas indicate accumulations of floating plastic debris.
So, just to summarize what we learned so far from our ESA Discovery project on remote sensing of plastic and marine litter, well, what we learned is that large accumulations, as in landfills, but also in our case, riverine floating debris and riverine floating plastic debris as well, can be detected by satellite sensors. We could cluster in the feature space plot of two spectral indices, and that gave us some confidence that plastic and mixtures with plastic can be separated from other end members, and that we can also classify by thresholding. Now, an immediate follow-up from this is to test the sensitivity of this thresholding to the background. But another question that we have is, can we really distinguish, without knowing beforehand which material we have, plastic from other floating debris? Well, remember that in using the floating debris index, we compared a relatively high reflectance in the near infrared against the baseline reference. And to better distinguish plastic, we should compare this high reflectance in the near infrared with low reflectance signals from the diagnostic plastic absorption bands. So the diagnostic plastic absorption caused these low reflectances, and that would then be your reference. However, in water or on land, when the plastic is wet, these diagnostic shortwave infrared bands and absorption signals get obscured by the water absorption. So that makes it a bit difficult, but and the strength of the plastic signal in these wavelengths will depend on the surface of the pixel that is covered by dry plastic. Also, we tested the microwave, so radar images. And against the riverine background, we found that the microwave C-band and X-band images show floating debris accumulations primarily as rough patches, so a high backscatter. But for further analysis, we need, of course, to capture these dominant plastic scattering signals against various backgrounds. If you want to extend to the sea, also wave and also other current conditions. And such studies have been done in the ocean wave test facility of Deltahuis.
If we consider remote sensing in the broader sense, meaning not only satellites but also lower altitude platforms such as drones or even ground stations, as it's the case of fixed cameras, we can see that there is a great potential in using these platforms to better monitor the problem of plastic pollution. And one of the most valuable aspects is that we can actually use remote sensing across the full journey of plastic litter from the point where it's generated until the sea. It can be applied, for example, to help identify and map the land-based sources from where plastic litter can be released. It can also help to quantify and characterize plastic litter in rivers, which work as pathways of transport into the sea. And finally, it could also be applied to help monitor the state and the fate of pollution in the sea particularly when we talk about large floating accumulations. Naturally, the different remote sensing platforms will have distinct applicabilities and limitations, but they can complement the current in situ observations and other assessment tools and provide valuable data to fill in particular knowledge gaps on an issue that is so complex. So let's zoom in into specific examples. Very often, local and national authorities lack basic data on the location and size or even the existence of dump sites. In addition, we are currently lacking critical information on how much plastic waste escapes from the different land-based sources, for example, transported by wind and runoff. Such information could be directly used by authorities to track and monitor the expansion and the shutdown of dump sites, and with this identify the points for intervention and priorities for investments, such as the upgrades in landfills. This data can also be used as inputs in modeling studies that account for point sources and leakages, for example, those sources that are nearby water bodies. And finally, ground-fixed cameras could potentially document the leakage rate of different types of plastic under certain conditions. Let's look at another example. As mentioned, we have very limited data on the amount of plastic waste that is leaking into the environment and how much plastic waste is entering a particular riverine system. But once in the river, plastic is then subject to many different processes that are very difficult to quantify. For example, how much plastic is retained in the vegetation of the river or in the riverbeds? Where does it accumulate? What is the fragmentation rate? And so on. And these processes, apart from being complex, can be very specific to that particular river or the local conditions. So in this sense, satellites can potentially generate these large spatial and temporal patterns that can help us understand the dynamic of some of these processes. For example, by identifying where and under which conditions plastic waste tends to accumulate. On the other hand, lower altitude platforms such as drones and fixed ground cameras have the potential to generate this more refined and detailed temporal spatial information and even enable the identification of specific types of litter. So why is this important? This data cannot work in isolation, but can potentially be integrated and strengthen other data as well as assessment tools. And in this integrated way, to try to make sense of how specific waste management practices, as well as environmental processes such as hydrology, are influencing and explaining the amounts of plastics found in a certain part of the river. Another example is the usage of this data to help calibrate, so attributing parameters for these different processes like the retention and accumulation and fragmentation, which are important when we're trying to simulate what happens to plastic once in the riverine system. And potentially, this type of data can also help us to then validate the outputs from this modeling. So overall, of course, again, not working in isolation, but integrated, remote sensing data can support and generate more reliable and realistic estimations of discharge of plastic into the sea, as well as how these vary throughout the year, within seasons, or even on a daily basis. And finally, detailed information about litter items can help to formulate specific targeted policies, for example, restricting the market of certain types of plastic, such as plastic bags, plastic bottles, and so on, as well as to help monitor the impact that these measures had in the occurrence of plastic in the environment.
Continuing the discussion about how remote sensing, and in particular satellite remote sensing, can help filling some knowledge gaps, we have some suggestions for future satellite missions. To distinguish plastic, multiple instruments on one platform, the multi-sensor platform, in constellation with the Sentinel-2 or Sentinel-1 monitoring satellites would be ideal for monitoring landfills, accumulations or hotspots. Sentinel-2 and Sentinel-1 can then provide the detection of anomalies, which are the accumulations that likely contain plastic, and Sentinel-1 can do it for most weather conditions. Our multi-sensor platform should have high spatial and spectral resolution and high signal-to-noise, and data processing from these sensors should focus on the anomalies, and the anomalies that we get from Sentinel-1 or Sentinel-2, to optimize the processing resources. The main sensors on this multi-sensor system or platform would be hyperspectral or multispectral sensors with also some narrow bands in the visible near-infrared and shortwave infrared. But other ESA discovery projects may come up with additional wavelength ranges or sensors that may support and increase confidence in the ultimate plastic classification. Our multisensory platform would be part of an integrated marine debris observing system, as proposed by earlier by Nikolai Maximenko et al. in 2019 already, and we propose to extend this, so to come up with a debris observing system that also contains monitoring of the riverine litter, and also including the interface with land, from which most plastic leakages originate. Finally, we would like to thank everybody who contributed to the Plastic Monitor project and who supported this project.